All right, today we're going to take a look inside the engineer's toolkit. But we're not just talking about wrenches and software. We're talking about a journey in thinking, from just fixing what's broken to actually designing things to be perfect right from the start.
Okay, so let's put you in the hot seat. Imagine a critical system just grinds to a halt. Alarms are blaring, the pressure's on. What is the very first thing you do? Where do you even begin to figure out what went wrong?
Well, for a lot of people, the first instinct is to do the simplest thing possible. It's a method that's built on, one of the most fundamental questions we learn as kids.
And that method is the classic 5 whys technique. You literally just keep asking why to drill down to what you think is the root cause. Let's walk through this example with a robot. So first question, why did the robot stop? Because the circuit overloaded and blew a fuse. Okay, why did the circuit overload? Turns out the bearings weren't getting enough lubrication. Right, next question. Why not enough lubrication? Because the oil pump wasn't pushing enough oil through. And why was that? The intake was all clogged up with metal shavings. One last time, why was the intake clogged?
And there it is, our final answer. After just 5 questions, we have what looks like a clear, simple root cause. There's no filter on the pump, so the solution seems totally obvious, right? Install a filter, problem solved. Easy.
But is it really that simple? Did we actually find the real underlying problem, or did we just find the first easy answer that let us stop asking questions?
See, this is the problem. The very simplicity of a tool like the 5 whys is its biggest strength, but it's also its most dangerous weakness. It can lead you straight into what I like to call the simple trap. And what's happening here is really about human psychology. We all have something called confirmation bias. It means our brains are wired to look for answers that already fit what we believe. So when a simple process gives us an easy answer like no filter, our brain just goes, yep, that makes sense, and we stop digging, even if the real issues are still buried.
So let's just look at everything we missed by stopping there. The 5 whys found no filter, but it never made us ask the really important questions, like, hey, why wasn't there an alarm for low oil pressure in the first place? Where did those metal shavings even come from? That is not normal. And maybe the most important question of all, why was the filter missing? Was it left off during the last maintenance check? Was it taken off on purpose? We completely missed all these other potential problems.
And that's the big takeaway here. These simple cause and effect tools are fundamentally limited. They can only ever reflect what the people in the room already know. They play right into our confirmation bias, and they almost always lead you to a single, simple cause, which means you miss out on multiple opportunities to make the whole system better. To really solve complex problems, we need to go beyond what we already know.
So this brings us to the next big leap. Instead of just reacting to problems after they happen, what if we could actually build our expertise, our knowledge, directly into the design tools themselves?
This is the idea behind something called knowledge-based engineering, or KBE. The idea is to take all the wisdom and the rules of thumb from your most experienced engineers and literally teach them to your software. You're trying to automate the routine stuff and design out the mistakes before they ever even have a chance to happen.
And here's a look at how it actually works under the hood. A KBE system really has 3 main parts. You've got the knowledge base. Think of that as the library where all the rules and data live. Then you have the inference engine. That's the brain. It takes a problem and actually uses those rules to figure out a solution. And finally, you've got the interface, which connects it all to the engineer and to the other software they're using every day.
Okay, so that's the theory. But what does it look like when you put it into practice? How do you actually give a brain to the main tool of modern design, which is computer-aided design, or CAD?
Well, the really cool thing is that a KBE system isn't some totally separate program. It's designed to be woven right into how an engineer works. It can be fully integrated inside the CAD software, it can be embedded as a smart part of the design itself, or it can be coupled to it, like a powerful external brain that helps drive the design. The whole point is that the intelligence is always connected to the geometry.
And here is just a fantastic, real-world example of this in action. This is a locating jig. Its only job is to hold a part securely while it's being worked on. Now, normally, an engineer would have to manually pick out and place every single bolt, pin, and clamp. But with a KB system, the engineer just tells it what part needs to be held, and the system automatically designs the entire jig using all of its built-in knowledge about what makes a good design. It's not just about being faster, it's about being smarter.
So building knowledge into our design tools is a huge step in preventing failures. But in really high-stakes fields like aerospace, just preventing failure
isn't good enough. The real goal is the pursuit of absolute physical perfection.
So let me introduce you to a process called hot isostatic pressing, or HIP for short. This is some truly wild stuff. You take a critical component and you subject it to just unbelievable conditions. We're talking temperatures up to 2,000 degrees Celsius and pressure that's 2,000 times the atmosphere around us right now. And the reason you do this is to literally crush any microscopic flaws or voids right out of existence, creating a part that is perfectly solid.
And this process is an absolute game changer for modern manufacturing, especially for things like 3D printing. Just look at the difference it makes. A standard 3D printed part has tiny little pores inside, and its strength can be different depending on the direction you pull on it. But after the HIP process, it becomes completely dense and what we call isotropic, meaning it's just as strong in every single direction. The end result is a massive increase in how long it can last, which, is pretty critical if that part is inside a jet engine.
So, we've covered a lot of ground, haven't we? We started this journey with an engineer just staring at a broken machine, and we've ended up with technology that can create physically perfect parts for spacecraft.
This really sums up the whole story. The way we approach engineering problems has evolved. We've gone from just asking simple questions after things break to understanding the mental traps that hold us back. From there, we've moved on to building proactive, intelligent systems that design things right the first time. And finally, to manufacturing processes that can achieve a level of quality that was honestly unimaginable not that long ago.
And this whole evolution from simply fixing to actively perfecting leaves us with a really fascinating final thought. We've proven we can capture expert human knowledge and teach it to our tools to build better physical things. The real question is, what other incredibly complex problems, maybe even problems way outside of engineering, could we teach them to solve next?